Hello everyone. In this video we are going to see how the disturbance could be rejected for a closed loop system using the frequency domain analysis. In general, the process disturbance d of t isn't a constant signal, but it's not varying at a high frequency as well. So usually d of t, dh of t as well, it has low frequency components, let's say. In addition, we also have d of t as the output of a system, which we call as HP of s, and it represents a part of the process dynamics, GP, and HP usually has a low-pass filtering effect. And as a result, what we get as the output of the HP of HPS, indeed, which is dt, the disturbance signal, it has usually harmonic components at low frequencies. So when we discuss about the disturbance, usually we consider low frequencies, okay? And then in order to attenuate the effect of dt at these frequencies, and we will consider a frequency as omega d, omega is smaller than omega d indeed, for the range of the harmonic components of the disturbance, we must remember that the effect of d on s depends on s of s. So as you can see over here as well, we have c over d equal to s the sensitivity function. And s of s sensitivity function is equal to 1 over 1 plus L of s. This is something that you should remember from the previous lectures. Therefore, we need to have the amplitude of s of j omega being small for this range of frequencies. If we want to have the attenuation factor as gamma d, which is in between 0 and 1, then we need to have this amplitude of s of j omega being smaller than gamma d for the range of frequencies that we have. On the other hand, we want to obtain this property, to check this indeed property, the disturbance rejection, by looking directly at the amplitude of L of j omega. We don't want to draw the amplitude for S of j omega and then determine the disturbance rejection property, similar to what we did for the noise attenuation. So we want to focus on the amplitude or body diagram of L of j omega and then discuss the disturbance rejection. We should also remember that we have, for small frequencies, we have the amplitude of L of j omega usually much bigger than 1, and for high frequencies it is much smaller than 1. This is an assumption that we had in the previous lecture. And omega c is the crossover frequency. Then if we find out the amplitude of S of j omega, it will be equal to amplitude of 1 over 1 plus L of j omega. For high frequencies, since amplitude of L of j omega is small, it's much smaller than 1, we can neglect it compared to 1, and as a result we will get 1 for the amplitude of S of j omega. For low frequencies, we know that amplitude of L of j omega is much bigger than 1, therefore we can neglect 1 at the denominator this time, and if we neglect 1 at the denominator, we will get 1 over amplitude of L of j omega. In terms of decibel and amplitude of S of j omega will be equal to 0 dB for omega bigger than omega c, and it will be equal to minus amplitude of L in terms of dB for low frequencies. And you can see an example over here. What we have in blue is the amplitude of L, and what we have in red is the amplitude of S, the sensitivity function. The crossover frequency here is at this point, and you can see that for frequencies, for high frequency parts, let's say, we have 0 dB for the amplitude of S, and for low frequency part, amplitude of L is minus amplitude of L, and you can see it over here. Then we also have the behavior of S of j omega as a high pass filter. It is able to replicate only the high frequency components of D on C, but since D doesn't have high frequency components, we are fine with that. We want just to filter the low frequency components of dt. If we assume that omega d is smaller than omega c, the crossover frequency, then for omega is smaller than omega d, we will have this condition. If we want to have amplitude of S smaller than gamma d, it means that we would like to have amplitude of L being bigger than 1 over gamma d. And this is the case because we know that amplitude of S at low frequencies is equal to 1 over amplitude of L of j omega. And in decibels, since we want to have amplitude of S smaller than gamma d, amplitude of L should be bigger than minus gamma d in dBs. Finally, we have the general case in which for very low frequencies, we know that amplitude, indeed the S of j omega, as omega goes towards 0, will be equal to 1 over 1 plus L tilde, because S is equal to 1 over 1 plus L. And L tilde here is the generalized gain of L of S. Therefore, for type 0 systems, if we assume that L tilde is bigger than 0, it is positive, then the limit that we have here will have a finite value, and it will get smaller and smaller as the value for L tilde increases. For type 1 or higher systems, the limit will be equal to 0. So as omega goes towards 0, limit of S of j omega will be equal to 0 because L tilde, because of the type of the system, which is 1 or higher, and there are poles at the origin. Here we have an example regarding the rejection of the disturbance. This is indeed a similar example that we had for the attenuation of the noise. You can see here that in the first graph, we have k equal to 1. You can see small kind of fluctuations over time. It's not that visible, but we have somehow the fluctuations with low frequencies. In the second graph, k is equal to 0.1. It means that the amplitude plot for L of j omega has moved downwards by 0.1 or minus 20 decibels, 20 decibels indeed. It has moved down by 20 decibels, and as a result, the effect of disturbance rejection is not improved. Now we have, you can see the effect of the disturbance in the second graph. If you compare these two with each other, you can see that the disturbance is not rejected properly in the second graph. For the third case, k is equal to 10, meaning that the amplitude graph plot for the L of j omega is moved by 20 decibels upwards, and you can see the effect of the disturbance is not visible in the third case. So in terms of rejecting the disturbance, we would like to have higher values for the amplitude at low frequencies. This is what we desire, because we need to have, we have it over here, yeah? We need to have amplitude of L of j omega being bigger than minus gamma d. So the bigger the value of L of j omega at low frequencies, it is better for us in terms of disturbance rejection. Alright, so over here in this slide we have a kind of conclusion for the disturbance rejection and noise attenuation. If we assume that omega c, the crossover frequency, is between omega d and omega n, Omega d and omega n are the frequencies that we have for the disturbance rejection and noise attenuation. Then in order to attenuate n of t, the noise signal, our factor gamma n for frequencies larger than omega n, we need to have the amplitude of L of j omega smaller than gamma n for those range of frequencies. In order to attenuate d, our factor gamma d, the disturbance, we need to have the amplitude of L being bigger than 1 over gamma d for the range of frequencies that we have here. And you can see the conclusion in a graphical way. So basically for the disturbance rejection and for the noise attenuation, we will have the dangerous zones. Amplitude of L of j omega should not enter these zones in order to satisfy the requirements in terms of the disturbance rejection and the noise attenuation. Something that you need to keep in mind here is that for the noise attenuation, we have a frequency omega n, and we have, in terms of the amplitude of L of j omega, we will deal with gamma n. For the disturbance rejection, we will have omega d, and this value will be equal to 1 over gamma d, or in terms of decibel, it will be equal to minus gamma d dB. Alright, so when you design the controller later, you will keep this in mind. If we have a requirement in terms of the noise attenuation and disturbance rejection, first we will determine these dangerous zones, and then we will try not to enter into those dangerous zones. And if we do so, we'll be fine in terms of the disturbance rejection and noise attenuation. Alright, so I think that's all for this video. In the next video lecture, we'll discuss about the step response parameters of the closed loop system referring to the frequency response of the open loop system. Thank you for watching and see you in the next video.